So if you just take a second and look at the smartphone in your hand, or, think about the massive server farms that are storing literally all your photos, the algorithms curating your social media feeds.
The literal cloud, right?
Yeah, exactly, the cloud. We talk about it every single day, and we tend to visualize this digital world as something, well, completely weightless.
Oh, absolutely. Like it's just vapor.
Right, just pure information sort of invisibly floating through the air around us. But when you actually trace that digital infrastructure all the way down to its roots, you don't find magic, and you definitely don't find vapor. You find something incredibly heavy, profoundly ancient, and just entirely physical. You find rock.
Yeah, it really is the ultimate grounding reality of the modern world. I mean, every single line of code ever written is, at the end of the day, processed by a stone.
Which is exactly what we're exploring in this deep dive.
Okay.
Okay, let's unpack this because we are looking at an element with, honestly, the ultimate double life.
Element 14.
Right, element 14 on the periodic table, silicon. We're going off this really fascinating research document, simply titled silicon.pdf. And our mission today is to figure out how this ordinary rock became the foundation of modern human intelligence. Because on one hand, it's ancient stone, right? It's the jagged gravel on a mountain, it's the sand at the beach. It's literally the dirt under your fingernails.
Yeah, it's everywhere.
But then on the other hand, it is this hyper-futuristic chip inside the device you are listening to right now. It is the absolute foundation of artificial intelligence. And I promise you, by the end of this deep dive, the way you see a window, a handful of sand, or, your own laptop, it is going to be completely different.
It really is. And to really grasp how a rock ended up processing complex mathematics, you kind of have to start with how that rock was formed in the first place.
Right.
Because it didn't just appear out of nowhere. And it wasn't around at the very beginning of the universe at all.
Which is such a huge misconception, right? Because I feel like people just assume the Big Bang spilled the entire periodic table out into the void all at once.
Oh, yeah, just a big explosion of everything.
Right. Hydrogen, oxygen, gold, silicon, just this massive cosmic soup from day one.
Yeah, but the reality is much more structured than that. The Big Bang essentially just gave us hydrogen, helium, and like a tiny bit of lithium. Yeah. That was it.
Wow.
Yeah, the early universe was really just vast swirling clouds of gas. So to get heavy solid elements like silicon, which by the way has an atomic mass of about 28, you need a factory. And the universe's only factories are stars.
Okay, so gravity pulls all that hydrogen gas together.
Right.
It crushes it, ignites it, and boom, you get a star.
Exactly. And for billions of years, a star survives by basically crushing hydrogen atoms together to make helium.
Right.
That's nuclear fusion.
Right, the engine of the star.
Yeah, and it releases energy, which pushes outward, fighting the inward crush of gravity. But eventually, the star runs out of hydrogen.
Right.
And when that happens, gravity starts winning. It crushes the core even harder, driving temperatures unimaginably high until the star actually starts fusing helium into carbon, and then carbon into oxygen.
So it's basically just stepping up the ladder of the periodic table as the pressure cooker gets more and more intense.
Precisely. And in massive stars, we're talking those heavier than like 8 of our sun's things get truly extreme toward the very end of their lives.
How extreme are we talking?
Well, when the star has exhausted almost all its fuel, the core reaches roughly 3 billion degrees.
Oh my God.
Yeah, 3 billion. And this triggers what astrophysicists call the silicon burning phase. The star starts fusing those lighter elements to forge just massive, massive amounts of silicon.
Wait, so how long does a star stay in that phase? Because like you said, it spends billions of years just burning hydrogen.
Right. The silicon burning phase lasts about a single day.
Wait, one day. Just about a day, yeah.
You're kidding. No, it is the frantic dying gasp of a giant star. It's incredibly fast. And once the silicon fuses into iron, fusion stops producing energy, gravity just instantly wins.
Boom.
Yeah, the core collapses in a fraction of a second, rebounding in a massive explosion, which is a supernova. And that explosion blasts all that newly forged silicon out into the cold vacuum of space.
That is wild. So every single grain of sand at the beach, every piece of quartz, every glass window, and like the microchip in my phone, it was all manufactured in a single chaotic day inside a dying star.
Yes.
And then just shot across the galaxy like shrapnel.
Well, exactly. And if we connect this to the bigger picture, the arrival of silicon represents this really profound turning point in the history of the cosmos.
How so?
Because before heavy elements like silicon became abundant, the universe was largely a plasma and gas phenomenon. It was swirling, it was hot, it was fluid. But silicon is highly reactive with oxygen, and together they form silicate minerals. So the sheer abundance of silicon meant that when gravity pulled stardust together to form new planets, there was actual solid material to work with. It's basically the moment the universe finally became mineral.
That is amazing. It's like it allowed the universe to build a physical floor
Hmm.
to actually stand on. It's basically the ultimate cosmic construction material.
It really is.
And you look at our own,
Hmm.
silicon forms the literal skeleton of the Earth.
Yeah.
I mean, if I'm remembering the geology right from the source document, something like over 90% of the Earth's crust is composed of silicate minerals.
Oh, yeah. It is absolutely the defining framework. It's in quartz, feldspar, mica, clay. Like, if you go outside and see a mountain of granite or a huge cliff of basalt, you are literally looking at massive silicon-oxygen structures.
Right.
And its most famous and, well, simple compound is silicon dioxide, which we usually just call silica.
And because it acts as the physical skeleton of the planet itself, I guess it makes perfect sense that humanity naturally reached for it to build the skeleton of human civilization,
Oh,
right?
exactly.
Though, we always talk about the Silicon Age as this very modern 20th century phenomenon. Like we picture clean rooms in California in the 1960s.
Right, Silicon Valley.
Yeah. But looking at the timeline of human development in the source material, I mean, haven't we always been in a Silicon Age?
We really have. The historical continuity is just striking. We absolutely have been. The modern digital era isn't some sudden departure at all. It is just the latest, the most refined chapter of our relationship with this one specific rock.
Right.
Because the earliest era of human civilization, what we think of as the stone, glass, and clay era, that was built entirely on raw silicon compounds.
Right, because, I mean, an arrowhead is just shaped silica. A clay
Really?
plot is just a hydrated aluminosilicate.
Bricks, mortar, concrete. Like the Romans built the Pantheon out of a concrete mixture that relied heavily on volcanic ash, which is incredibly rich in silica.
Wow.
And perhaps the most crucial leap for human knowledge was learning to take that silica sand and melt it down to create glass.
Which completely changed how we interact with the world. Because without glass, you don't get lenses.
Exactly.
And without lenses, you don't get microscopes to discover bacteria. And you don't get telescopes to figure out our actual place in the solar system. Glass is basically what let us actually see the universe.
So we spent thousands of years mastering the macrostructures of silicon, right? We stacked it into walls, molded it into pots, melted it into lenses, but the shift from an industrial civilization to an informational one, from stacking rocks to literally making them compute, that required a massive leap in how we understood the element on an atomic level.
And this brings up what is probably the most fascinating and honestly the most confusing part of the whole story for me. Because I can wrap my head around melting sand into glass. That makes sense.
Sure.
But how on earth do you take a rock, purify it, and then teach it to do math? Like, how do you turn a stone into a thinking machine?
Well, to understand the mechanism there, we really have to look closely at silicon's chemical personality. On the periodic table, silicon sits directly on the dividing line between metals, like copper or iron, and nonmetals, like oxygen or carbon.
Okay.
It is what chemists call a metalloid.
Meaning it sort of has an identity crisis.
In a way, yeah. It looks shiny and metallic, but it's brittle like glass. But most importantly, its position governs how it conducts electricity.
Right.
Metals are conductors, right? They let electricity flow freely. Think of a copper wire.
Sure.
Non-metals, like rubber or wood, are insulators. They block electricity entirely. But silicon, sitting right in the middle, is a semiconductor.
Here's where it gets really interesting, though, because a pure silicon crystal doesn't just semiconduct on its own, right? Like, and I just run a current through an absolutely pure block of silicon, nothing happens. It actually acts like an insulator.
Exactly. And that is the absolute secret to its power. Pure silicon is incredibly stable. It has 4 electrons in its outer shell. And in a pure crystal, every single silicon atom neatly shares its electrons with its 4 neighbors.
Okay.
So it forms this perfect, tightly locked grid. There are no free electrons wandering around to carry an electrical current. It's just completely locked down.
Okay, so let's try to visualize this. Imagine pure silicon as a highly packed, sliding tile puzzle.
Okay, I like that.
You know the kind where you have a little plastic frame filled with square tiles? But in this case, every single space is filled. There's no empty square.
Right.
So no matter how hard you push on the tiles, nothing moves. The grid is totally frozen. That's our pure insulating silicon.
Yeah, that's a great framing. The electrical current pushes, but there's just no room for movement.
So to make it conduct electricity, engineers use this process called doping. They introduce a tiny, precise impurity into that perfect grid, kind of like bribing the bouncer at a highly secure nightclub. They might swap out a few silicon atoms and replace them with an element like boron. Now, boron only has 3 outer electrons, not 4.
Which means suddenly there's a missing electron in the crystal lattice.
Right, so back to our sliding tile puzzle.
Yeah.
Doping with boron is like popping out one of the tiles. Suddenly, there is an empty space, a hole.
Right.
And because there's a hole, the other tiles can slide around. Electrons can move, so that frozen grid suddenly becomes fluid.
That's called p-type doping because the missing electron basically acts as a positive charge. And the alternative to that is n-type doping, where engineers inject an element like phosphorus.
Okay.
Now, phosphorus has 5 electrons. That forces an extra unattached electron into the grid. So in your puzzle analogy, it's like dropping a loose marble on top of the tiles that can just roll around freely. It carries a negative charge.
So you have these 2 modified pieces of rock. One has empty holes waiting for electrons, and the other has extra electrons looking for a home. If you just stick those 2 pieces together, what happens?
Well, you've just created a PN junction. And honestly, this is where the magic of the digital age truly begins.
Wow.
Yeah, because when you place them together, you create this microscopic environment where electricity can only flow easily in one direction. But even more importantly, by adding a 3rd layer and applying a tiny voltage to it, you can actually push those electrons or holes around.
Right.
You can actively open or close the path for electricity. You have created a transistor.
A gate that can be opened or closed, not by like a physical hand flipping a switch, but by applying another electrical signal.
Precisely. It's a switch with literally no moving parts. Just an immovable, solid crystal where electrons are corralled across atomic borders.
But we still have to bridge the gap between a simple electrical switch and, a machine that can actually process an algorithm. Like, how does turning a microscopic electrical current on and off actually equate to computation?
What's fascinating here is how human logic perfectly maps onto physical circuits. Let's look at a really simple logic gate, specifically an A&D gate. Imagine a pipe carrying water, and there are 2 valves in a row on that pipe, valve A and valve B. For water to actually reach the end of the pipe, both valve A and valve B must be open.
Right.
If only A is open, the water stops at B. If only B is open, the water never gets past A.
So the physical design of the pipe enforces a logical rule. Both conditions must be met. True A&D true equals true.
Exactly. Now just replace the water with electricity and replace those physical valves with our tiny silicon transistors. You have literally physically built a rule of logic out of rock.
That is wild.
Right. If you apply voltage to transistor A, turning it on, or making it a 1 A&D, you apply voltage to transistor B, also a 1 current flows out. If we define current flowing out as another 1, we've just created a system where 1 and 1 results in 1.
And by arranging different types of these gates like OR gates, where only one valve needs to be open, or NOT gates, which completely reverse the flow engineers figured out how to physically add binary numbers.
Exactly.
Just cascading thousands and then millions and now billions of these microscopic gates.
Billions of them, all etched into a single wafer of silicon that's no bigger than your fingernail. When you send an email or ask an AI a question, you are basically sending a pulse of electricity through billions of sequential silicon gates. The path the electricity takes through that maze is the math.
Wow.
The rock doesn't know it's doing math, right? The rock is just channeling electrons through a labyrinth that we carved into its atomic structure.
It's staggering to think about.
Yeah.
We took the exact same material we used to build brick walls and glass windows, but instead of shaping it with a trowel, we learned to shape it at the atomic level.
Yeah.
But, getting to that level of purity, getting silicon so perfect that we can control individual electrons, that is not a clean or easy process at all.
Oh, no. It's one of the most resource-intensive processes on the planet. We tend to think of the digital economy as this green alternative to the industrial economy. Like, we aren't burning coal in our living rooms anymore. We are just streaming video.
Right.
But the infrastructure behind that streaming requires a really intense physical toll on the Earth.
And it starts right at the source, right? The sand itself. Because I always used to wonder, when I'd read about global sand shortages in the news, how that was even physically possible.
Yeah, it seems counterintuitive.
Right, because we have the Sahara Desert, we have the Mojave, we have millions of square miles of dunes. How could we possibly ever run out of sand to melt down for silicon?
Well, it comes down to the actual physical and chemical properties of the sand. Desert sand is effectively useless for our structural and industrial needs.
Really?
Yeah, because in a desert, the sand grains are constantly blown around by the wind, crashing into each other. Over time, that wind erosion polishes the grains until they are perfectly round, almost like microscopic marbles.
Oh, and you can't build with marbles. They don't interlock.
Exactly. If you try to mix perfectly round sand into concrete, the structure just crumbles under pressure. So for construction, you actually need water-eroded sand from riverbeds or ocean shores. Water acts differently, It chips and fractures the grains, leaving jagged, angular edges that lock together tightly.
Okay, that makes total sense for the construction side. But what about for microchips? Does a microprocessor really need jagged sand?
For microchips, the issue isn't really the shape of the grain, it's the intense chemical purity. You cannot just scoop up random desert sand, which is full of iron and calcium and organic matter, and expect to build a working semiconductor.
Right.
To make a modern computer chip, you need ultra-pure quartz. You need silica sand that is nearly 100% silicon dioxide. And those highly specific geological deposits are very finite. They're aggressively mined, which leads to habitat destruction and severe river ecosystem disruptions globally.
And getting the sand out of the ground is just step one, right? Then you have to actually refine it.
Oh, and the refinement process is brutal. To separate the silicon from the oxygen, you have to heat that quartz sand with carbon in massive arc furnaces at over 2,000 degrees Celsius.
Wow.
Yeah, and that produces metallurgical grade silicon, which is maybe 99% pure.
Which is fine for mixing into aluminum alloys or making solar panels.
Right.
But 99% is basically garbage if you're trying to build a microchip.
Exactly. A single stray atom of iron or copper in a silicon wafer will completely short-circuit those microscopic transistors we talked about.
Right.
So semiconductor-grade silicon needs to be 99.9999999% pure. We call it 9 nines purity.
That is insane.
It is. And to achieve that, the raw silicon is dissolved into highly toxic gases like trichlorosilane, distilled, and then carefully grown into massive, perfect crystals in a vacuum.
And the chip fabrication plants themselves, the fabs, are some of the most complex, expensive buildings humanity has ever constructed. The source points out they consume millions of gallons of ultra-pure water a day just to wash the silicon wafers between chemical baths. They draw massive amounts of electricity.
It really forces a perspective shift, doesn't it? The cloud is heavily subsidized by the physical Earth. Every query you run, every digital interaction, it all relies on heavily mined, hyper-refined, chemically treated slices of planetary crust operating in buildings that literally consume more power than some entire cities.
Realizing how much physical Earth we rely on just to sustain our digital lives really makes me look at our own biology differently. Because we are walking, thinking beings entirely built out of carbon, but our civilization is entirely propped up by silicon.
The comparison between carbon and silicon is so profound, especially because they're actually cousins on the periodic table.
Oh, right.
Yeah, they sit in the exact same column. They both have those 4 outer electrons, meaning they both love to form massive complex frameworks.
But they took completely different paths in the real world. We don't see silicon-based life walking around outside of science fiction movies. Is there any biological role for silicon on Earth?
There is, but it's very different from carbon's role. Carbon is wildly flexible. It bonds with almost anything, creating the complex, dynamic molecules needed for proteins, fats, and DNA. Carbon is basically the engine of metabolism.
Okay.
Silicon, because it's slightly larger and forms more rigid bonds, well, it isn't great at the chaotic chemistry of living cells.
It's too stiff.
Exactly. So biology uses it for structure instead. You see it in the rigid stalks of bamboo or certain really tough grasses. In human bodies, trace amounts of silicon are actually involved in synthesizing collagen for our connective tissues and bones. But the most stunning biological use of silicon is in the ocean, with microscopic organisms called diatoms.
Oh, the ones that build the glass houses.
Yes. Diatoms extract dissolved silica from seawater and construct these incredibly intricate, beautifully symmetrical shells around themselves. Under a microscope, they look like microscopic crystal cathedrals. It's life-taking rock and literally turning it into armor. But again, the silicon is purely structural. The life inside the shell is still carbon.
So what does this all mean? We have these two sister elements. Carbon became the architect of life. Silicon became the architect of structure.
Carbon became biology, silicon became technology.
And you can really see how those two paths finally collided in the modern era. Because carbon, meaning us, human beings, we generate thoughts. We generate memories, culture, science, and logic. But carbon biological memory is fragile.
It is.
We forget things. We die. Our brains cannot hold the sum total of human knowledge. So our relationship with silicon reveals this desperate, brilliant human desire to externalize our minds.
We took the logic that was firing in our carbon neurons and we carved it into the rigid, permanent structure of a silicon crystal.
We took our memories and put them into flash drives. We took our visual history and put it on servers. We took our ability to calculate and outsourced it to microprocessors. We basically figured out how to make our thought process live safely outside the fragile human brain, scaffolded in a quiet, durable stone.
It's why silicon is classified as a Tier 1 civilization dependency. It is the material anchor of the modern world. If you were to somehow magically erase refined silicon from the Earth right now, it wouldn't just be that we'd lose our smartphone.
Right, so much bigger than that.
The global financial system instantly halts, the power grid fails, global supply chains disappear, the medical field steps back a century, our ability to generate renewable energy through solar panels vanishes. Our planetary civilization is really a symbiosis between carbon intelligence and silicon infrastructure.
It's the material that allowed the Earth to become a thinking machine. And keeping all that in mind, the stellar origins, the massive mining scale, the microscopic physical logic gates, I want to leave you with one final thought, something to chew on long after this deep dive is over.
Oh, I like this.
Think about the sheer volume of our lives that is now stored exclusively on this processed rock. From our most intimate photos to the vast archives of our scientific achievements, millions of years from now, long after the server farms have crumbled and the data centers have been buried by time, when future explorers, or whatever intelligence comes next, digs down into the Earth's crust to understand who we were, will they learn about our civilization by finding the fossilized carbon of our bones? Or will they learn about us by finding our fossilized memories, forever trapped in the silicon sand?